Section 12.2 Binary Classifiers. A binary classifier is a function which can decide whether or not an input vector belongs to some specific class. For example, spam and ham. In the context of email and online communication, spam refers to undesired bulk messages, while ham refers to desired emails. Binary classification is often considered as two-class classification, one class inside and the other class outside. It is a type of linear classifier, which means that the classification algorithm produces its predictions based on a linear predictor function. Linear classifiers are a sort of artificial neurons. Examples are perceptron, Adeline, logistic regression, and support vector machine. We'll consider them later on. Neurons are interconnected nerve cells involved in the processing and transmitting of chemical and electrical signals. Look at the figure. Multiple signals arrive at the dendrites. They are integrated into the cell body. And once the accumulated signal in magnitude is larger than certain threshold, then an output signal is generated and transmitted to the next neuron. Okay, we have a definition. YI is labeled data, and with X is in d-dimensional. Each point is in d-dimensional space, and labels are either 0 or 1. So we have two-class data set. A binary classifier finds a hyperplane in RD that separates data points into two classes, as in this figure. Practically, the machine learning algorithm will generate such a hyperplane, so that once a new point comes and one side, then we can classify the point. In this case, this point will be a positive point. Okay, we have observation. And most of our binary classifiers are along with an objective function. And now for binary classifiers, the labels 0 or 1 is chosen for simplicity. You can choose -1 and 1 or 0 and 1. Now, hyperplane can be formulated by the normal vector and a shift. So it'll decide the intercept, like this one. Now, for example, if you consider a line in the plane, and that will be now two component x1, x2, and w1, x1 plus w2, x2, and plus w0 is a line in the plane. To learn w and w0, we may formulate a cost function to minimize. For example, the sum of squared error can be formulated in this way. So for each point, we try to get a z-value, that is called the net input, and then along with some activation function, now the difference is the error, and now square sum is obtained for the objective function. And depending on how you choose this objective function or cost function and what the activation function is, the method are different. An important task in machine learning is on the choice of effective activation functions and cost functions. Now we'll begin a practical algorithm, and in modern society, Perceptron is not being used in this form. However, this is the earliest algorithm, so we need a little bit knowledge on this one. Perceptron, from 1950s, the algorithm was being used, and the inventor is Frank Rosenblatt. And here we have some detail about the algorithm. We can formulate the perceptron algorithm as a binary classifier in which we refer to our two classes as 1 and -1 as positive class and negative class for simplicity. Now there's input vector, d-dimensional vector, and weight vector to get net input. In training, we have to decide this weight vector. During the training, we find these values, and so that now, along with this net input, we can decide. Now here, the net input is larger than equal to certain threshold, then that is class 1 in a positive class, otherwise is negative class. So that is now at the end some activation. Of course, when we train the algorithm, now by using this activation function, we have to update the W values, and now once it is convergent, then we use that to predict the new points. Okay, this the thresholding can be considered changed into another form. Now, okay, now here theta, so the z is compared with the theta. So deciding this theta is also a problem. So we may, so the z, once it's the same, then it's the same as the theta. And in fact, larger than equal to theta, but we consider the equality, then we can see this one. Rather than putting this one on the right side, we move this one to left-hand side. Then it'll be minus theta, and we rename it along with the W0, so that that can be the net input along with W0 left-hand side, which is minus theta. And for this one, here, z is non-negative, then it can be 1, otherwise -1. So then this one, this thresholding, and this one will be the same. Now, rather than choosing theta yourself, now let the algorithm try to update and select the value so that it's simpler for you. And here, the equation, this equation equals 0, represents a hyperplane in this dimensional area, and W0 decide the intercept. So you can easily see that, for example, now W0 in two-dimensional area domain, W0, W1x1 plus W2x2 equals 0 will make a line right? That will represent a line in the two-dimensional space. So through update, the iteration will try to find the W0, W1, and W2 in Perceptron. Okay, here we have the Perceptron learning rule. It's given in this way. Initialize the weights, of course, W0 and W to 0 or small random values. Now, for each point, each sample xi, we try to update. So compute the output value, which means that it's predicted value. And then now compare with the original label. And now once they are different, then and this is a factor, and then xi and scaled by eta will be added to the old weight to get new one. And W and W0, along with this update rule, iteratively we try to refine the weights, and once it is convergent, then we can stop. Here, eta is called the running rate, which must be small, between 0 and 1, but usually it's order of 1,000th, so it must be small. Sometimes you can choose this one order of 100th, but usually it must be really small. If it is large, then the algorithm blows up. Okay, here we have the mind simulation, a thought experiment for the perceptron algorithm. Once the predicted the value is the same as original label, then there will be 0, so that and the weight remains the same, unchanged. However, once the wrong prediction, then which means that once it is 1, then a predicted value is -1, then this portion will be 2. If the label is -1, the wrong means is +1, so that this whole thing will be -2. So we can write the result in this way, ±2 eta xj for ith the point, so that eventually, along with this rule, the weight will be pushed toward the direction of the positive or negative target class. So by using this iterative update, we can get a convergence once a data set is separable. Okay, here we have an implementation, Perceptron for iris data set. Okay, here we have a class in Python, and once you make an object out of this class, then this will be initialized then along with this method and initialized, and we have to have your activation, which is thresholding, and fit is just a train, and that is predict, and that is now prediction. For new data set, we try to measure the accuracy, and then here score is computed. This is accuracy in the value will be between 0 and 1. The higher, the better. Okay, and that is implementation, and this portion is for figuring. I implemented this way to get the figure you'll see soon. You can implement your own algorithm and along with Python class. Then you have to include this activate, fit, and predict. Once you want to use your algorithm, your classification algorithm, along with some other built-in functions. For example, when you are using scikit-learn, the classification algorithms, then you have to have this method inside of your algorithm. Along with that, you can use your algorithm for ensemble methods, the combinations with some other algorithms. Okay, anyway, here now, along with that function, here we have now, here we have test along with iris data set from scikit-learn. You can find this one quite easily. And here, the iris data set has 3 classes, so that we only chose 2 classes. Now, why? The label will have 0, 1, and 2, so we collect only 0 and 1. And also here now among the all labels, we try to get only 0 and 1 labels. And also there are many features. The number of columns is larger than 2, but only we collect the zeros column and column 2, so that now here this is 2 class, 2-dimensional problem. So for that one, by using train test split is coming from here the scikit-learn model. Scikit-learn is very useful and a very popular algorithm. If you know this package, then your job market will be way better. Okay. Now, after splitting by using the train part, we'll try to train, and then now here feed and fig rather than fit, we are using the figure part to get such figures, and then accuracy is measured by using the score method. Okay, here we have the data set, this 2-dimensional 2-class data set. So we have X-shaped data points and circular shaped data points. The iteration, perceptron iteration start with 0 initialization. Okay, over there. And once iteration 0 is this one. And after 10 iteration is end with this one. And 20 and back here now. And 30, 40, 50. And in 30 iteration, here is given here, and 40, 50 the same. Once it is convergent, then it's not moving because it's through thresholding, it is updating. So that for every data point, it is satisfying, is correct decision is made, so that even though this separating line is not really perfect, and rather than and here this line, you may want to get a line here around the middle of the point bodies. So in the case, it can be better. However, anyway, this line is near around the bottom points, so it is not really ideal. However, anyway, and this line is separating all data points. So once it reaches at the point, then it's not being updated. Okay. Anyway, after 30 iteration, so it is after considering 30 data points, it is converged. And then now after that, it's not moving. This is the property of the perceptron. Okay, we'll continue in the second part. Thank you.